Hi guys, today we're going to talk a little bit more about unit conversion, especially when those conversions become more complicated. So this lesson was intended to teach you how to do this as if you were taking the Regents exam, which we know you aren't taking at the end of this year, but I would argue is still really important for next year because similar ideas show up in chemistry. So what I've done is I pulled up the Regents reference sheet. They give you several conversions here. They do not give you some of the basic metric conversions though. So how many, centimeters are in a meter, etc. You could technically take this sheet I gave you and Google these conversions. However, I would argue it's a good strategy to try out. Double check with Google. We'll go from there. So it says that you want to take 3.5 kilograms and go to milligrams. One strategy would be to go down a level at a time. So what I mean by that is get rid of the kilograms. So the next level down, so 1 kilogram, would be grams. So there's 1,000 grams in 1 kilogram. So the kilogram units cancel out. It's all the strategy is about is canceling. Then I could say, okay, I want to get to milligrams. Well, milligrams to grams. There are 1,000 milligrams in just 1 gram. So I'll choose that. Grams cancel out. And I know my conversion. All I have to do is go across and do the mathematics appropriately. In this case, I'm just multiplying 3.5, 1,000, and another 1,000. So it's 3.5 million milligrams. The next one, we're going centimeters to kilograms. And just reminders of the metric system, it's all about those prefixes. So centa means, I can think of it like century, 100. Kilo means 1,000. Milla, like millennium, means 1,000 as well, but the other way. So I have 430 centimeters. The next level, I guess you could say, would be meters. So for every 1 meter, there's 100 centimeters. Again, I chose to put it in this fraction form because I want the centimeters to cancel. I want them one to be in the numerator while the other's in the denominator. And then lastly, we can say there's for every 1 kilometer, because that's what I want to end up with, so I don't want that to cancel out. There are 1,000 meters. Notice the units cancel out appropriately. In this case, instead of multiplying by these larger numbers, I'm taking that 430, I'm dividing by 100, or multiplying by 100, and then dividing by another 1,000, or multiplying by 1,000. So it's 0.0043 kilometers. Again, if I was to do this quickly, I'd probably just Google it as my check and kind of go from there. This one's kind of funky. We're going standard English, so we got 54 yards, and we're going to centimeters. So do one step at a time. I say, okay, what do I know about yards? Well, and this is a good place to put this reference sheet into play. I know that there are 3 feet in 1 yard, so goodbye to yards. I know that there are 12 inches in 1 foot, goodbye to feet. And if I look at my reference sheet here, what else do they give me? Oh, here. 1 inch is 2.54 centimeters. So I can use that conversion factor as well. So 2.54 centimeters per 1 inch, goodbye to inches. This one, just go across, multiply those together, you get 4,937.77 centimeters. And the last one, this is actually really useful, especially if you're doing any kind of home construction or trying to figure out volume. Talks about the number one example I can think of, and you guys are thinking this is lame, but mulch. Okay, if you had to mulch flower beds, like you want to figure out how much mulch you need. So there's 144 cubic inches, so inches cubed, to cubic feet. It is tempting to say, okay, I have 1 foot, there's 12 inches in a foot, inches canceled out. But technically you have inches cubed divided by inches. So only one of the inches technically would cancel out, so you'd have inches squared. But you can still use that same multiplication factor, and this is really helpful, especially for higher level conversions, to say, you know what, I'll do it again. For every 1 foot, I have 12 inches squared. For every 1 foot, I have 12 inches squared. The unit analysis stays true. Feet times feet times feet, feet cubed, inches times inches times inches, inches cubed, goodbye to that. So for that conversion, I take 144 and divide by 12 cubed. You end up getting 0.08 feet cubed. So please try your best. Try to use the reference sheet. Try not to go to Google right away for things. I think it's worthwhile practice. The next example, classic regions problem, they're trying to trick you with all kinds of different information. So let's break down the problem. So you're making a wind turbine. A part for that. The volume of that is 1,015 cubic centimeters. Strategy, write some stuff down. Here's my writing things down. You can purchase steel, that's what you're gonna make it out of, for 29 cents per kilogram. I wrote that down, and I try to keep it in this consistent strategy because I know I wanna use this cancellation method. And the density is 7.95 grams per cubic inch. So let's see if I can combine things, what I need, and we'll go from there. I want to make 500 parts, so consider that. I want to go to the nearest dollar. So let's just find the cost of one part. So the cost of one part, you start with that volume. The next thing I know is I can pair these together to get rid of the cubic centimeters, convert to grams. So now I'm thinking, okay, I'm in grams. I don't want to stay in grams because I had this kilogram thing I got to somehow involve. But I do know 1 kilogram is 1,000 grams. So goodbye to grams now. So I've canceled these. I'll do all the arithmetic in a little bit. And then finally, I can put in this information. It costs 29 cents per 1 kilogram. And I can multiply the 1,015 times the 7.95, divide it by 1,000, multiply it by 29. To the nearest dollar, each unit's going to cost you $2.34. And then you can multiply that by 500, round to the nearest dollar. You do not have to do it exclusively with this method. That's just one way to combine all the information. I've also worked with a lot of students who like to take it a piece at a time. So go with that too. The back of your first note sheet doesn't match up to what I'm about to show you. But if you go to the next page in the packet, you'll see this on the back side of the blank piece of paper. So we're switching gears a little bit. This is called Cavalieri's principle. Yeah, I think I said that right, excuse me. So when I look at this, you're gonna be like, yeah, this makes sense. But it's a formal conceptual idea with volume. What it says is if you have a prism, okay, and we know when we have a prism, when I take a cross section, it has a consistent area. Every time I take a cross section horizontal to the base, or parallel to the base, So what it says is if you have two prisms, so I'm going to look at these first two in the figure, and no matter how you slice it parallel to the base, if they end up having the same area, that's one thing you need, no matter where, and they actually have the same height throughout, those volumes will be the same. Well, yeah, that makes sense. To me, this looks like a block of Post-it notes or pieces of paper you're playing with. If you just slant it, if you kind of pull the paper and mush it around, it's not going to change volume. So it's a nice thing to know, though, for kind of like funky looking oblique shapes. So all three of these shapes, because they're prisms, you're not taking anything away from them. The area of the cross sections are the same, and the heights are the same. You're just making them look a little bit different. Volume will stay consistent. This is a typical regions question. Okay, I know you're not doing this year, but bear with me. So it gives you two figures. They're both triangular prisms. You're like, okay, cool. No matter how I slice it parallel to the base, those areas are going to stay the same. They have the same height of 14. They want you to use this principle. So I really tried my best to explain, each base area, the height, how this relates to that principle, and use some of the same language. So figure A and B are both prisms. Therefore, any cross-section parallel to the base, we can congruent throughout the figure. So the base isn't necessarily the thing that's on the ground or on the bottom. It's the shape, whether it's this triangle here, that's carried throughout the figure. So what I mean by that is with a prism, you'll have two bases, and then you'll have these, technically they're rectangles that connect those bases together to make your height. So the base happens to be the triangle, hence the triangular prism. So this area of each triangle will be the same, will be 20 units squared. This area will also be 20 units squared. We know they have congruent heights. So I mentioned that. I said, hey, by Caravalari's principle, cross-sectional areas will be congruent at any height, which is key, and heights of these figures are congruent, so the volumes will be congruent. Not going to stress you out too much with this type of problem. I just wanted you to get some exposure. So that's it for now. See you in Google Classroom.